Welcome to Study Loop.
In this problem, we have a rod attached to a collar that is a rod attached to a collar. A collar attached to a rod that has a straight section here and then a circular section here. There is a spring connecting the collar to a point on ground, and I'm going to call that my origin in this problem. So we have this system set up, and we're asked to figure out a couple things about it. We want to know what the force, the normal force from the rod on the collar is at points A and B, which are at the top of the circle and the right hand side of the circle here. The weight of the collar is 10 pounds. The undeformed length of the spring is 14 inches. The spring constant is 4 pounds per inch, and the radius of the circle is 14 inches. So point C, relative to the origin here, is at minus 24 inches, or minus 28 inches and minus 14 inches. So minus 28 inches this way and 14 down. It has no kinetic energy here because it is being released from rest. Point B here is down 28 inches from the origin. And I guess I didn't write point A in here, but point A is down 14 and to the left 14 inches. Let's write that in here. RA equals minus 14, minus 14, 0 inches. Okay. So to figure out what the normal forces are, we need to figure out what the velocity is. So we can do that by just using conservation of energy. So we can write the energy at C, and this is in a vertical plane, so we need to be worried about the potential energy. Then we can write the potential or the gravitational potential, and then we can write the potential energy at A and then at B. And we have the kinetic energy at A and at B. And because there's no kinetic energy at C, we know the kinetic energy at A is the potential energy at C minus the potential energy at A, and the potential energy at B is the kinetic energy at B is the potential energy at C minus the potential energy at A. And that gives us an equation for VA, and this gives us an equation for VB. And we find that VA is 203 inches per second, and VB is 164 inches per second. So with those, we can then go and find the normal force. So we can get the acceleration. So the acceleration at point A has some component that we really don't care about in the x direction, and in the y direction, it is minus VA squared over r because it's on the circular part of the rod. And R is again 14 inches. At B, it's down, when the collar is down here, the normal force from the rod has to be in the horizontal plane. And it is the acceleration in that, or horizontal direction, and the acceleration in that direction is minus VB squared over R. And we also have some acceleration in the y direction, but we're not worried about that because the normal force has no component in that direction. So little free body diagrams at point A and point B. We have the spring force, the normal force, and gravity acting. And so we have the mass times acceleration at A is the spring force at A, plus the normal force at A, minus the weight. And so the normal force at A is in the vertical direction. So that just has a NA J component. The force, spring force here, we can figure that out. The magnitude is KLA minus L naught, and the direction is from from A to 0. So we can figure out that unit vector EA0 because we know point A is, and we know this is the origin. So we basically just need to figure out the unit vector And so we have our spring force, and then we can find the component of that in the vertical direction, and that gives us an equation for the normal force, and that normal force becomes 0 minus minus 82.4 pounds, and then 0 in the z direction. So that the normal force is actually pushing down on the collar. So the collar is pushing up on the rod. And then at B, again, the normal force is in the horizontal direction. The spring force is in the vertical direction, so we don't have to worry about that one in this case. And same with the weight. So in this case, the normal force is actually just going to be mass times this thing here, and we can calculate that, and that becomes minus 49.6 pounds in the horizontal direction and 0 in the other directions. So we have a force pushing the rod. The rod is pushing on the collar in this direction, and the collar is pushing on the rod in that direction.